Yeah, so I'm Joel Weisberg, and I have the honor of introducing Paul Grossi from class of '89. And just in case you don't like his talk, he's brought a lot of his own audience with him. So if you're a friend of his from Carleton days, would you raise your hand? If you're not ashamed to mention it. Yeah, I thought there were some people in the back that hadn't taken your class, Jade, the ones with gray hair. Okay, so, and he is a Renaissance man and a physics major, which I want you to know are not mutually exclusive, and that's part of why I love being at Carleton, because so many of the people in our department are Renaissance people, and I'm talking about the students, and I'm talking about the professors too. So he got his physics degree here, and then he has gone on to a career in teaching, and teaching broadly construed, science teaching broadly construed. He was part of an organization that would take recycled materials, and I think that's a kind word, and turn them into science kits for under-resourced schools. And he worked as a science educator at Stanford University for a while. And for the last about 4 years, he's been teaching science at a girls' middle school, at which his daughter attends, or has she already graduated? Yeah. So today, you and he are going to learn how to put on physics goggles.
It's a tremendous honor. Certainly when I was taking physics, I don't think it was 123 at the point that I took it, but I remember taking this class, and I could never really imagine myself as actually being behind the podium and presenting. So I'll just start with a little bit about kind of who I am and the path that I've taken. So as Joel mentioned, I graduated in '89, arrived in 1985 from the sunny shores of California. It was a very happy accident that I wound up at Carleton. And managed to make it through here in 4 years. Two of my roommates are here today from that Village House 110, and actually had dinner last night with some of the professors, and was reminded of the fact that Cindy Blah's home is actually adjacent to Village House 110, and she remembered us. It's probably not a good thing. So part of what I would like to do today is just apologize for any transgressions that we may have committed. So after sort of getting out of college and heading into the real world, which some of you were talking about in your last class, I realized that I really had no idea what I wanted to do. But I love physics, and so I wound up teaching, and at some point I met my wife, and we had a little girl, probably the happiest day of my life. She's now 14 and heading into high school, and I'm a middle-aged middle school teacher. And so I just want to talk a little bit today about kind of what that journey meant for me, and specifically in terms of coming from having been a physics major here at Carleton. So I'm going to try to answer what exactly physics goggles are, because it's really a phrase that came for me out of my development as a teacher. So kind of where things started for me was, as a teenager, I was fascinated by the night sky, and just sort of that sense of wonder, looking up and wondering how things worked and what was out there. And that was really cemented for me, an experience I had. After my junior year in high school, I went and did a program at Harvard and got to live in a dorm, and I came from a very little pond of a school, so I met lots of other interesting people. And one of them was redhead and very attractive, and we went up to the telescope one night and we saw Saturn. And I remember looking through and thinking, wait, that can't be real. Didn't actually do it, but wanted to go around to the other end of the scope and make sure they weren't dangling a little cutout piece of paper. Because it doesn't look like that through a telescope. This is a very dramatic image taken from a satellite quite close to the planet. It looks like this little paper cutout thing, but it was real, and I just had to know more. And so when I got to Carleton, and it was pretty clear that the only way I could take more astronomy classes was to become a physics major. And so I went through 4 years here and had some ups and some downs. And the last time I think I had to do a talk at Carleton, I had to jump into a snowbank prior to my Comstock because I was so nervous. I'm feeling a little better today, so good thing. And so I graduated with a physics degree, and I went out into the real world, and I was really struck by the kind of reactions I would get from people. You know, I would say, yeah, I was a physics major, and they would go, oh really, you must be really smart. Or, oh God, physics, I hated physics. And I was stunned by this, because to me, physics was like the coolest thing, and I could not believe that so many people didn't understand how cool physics was. And you know, so I started thinking about that. I had had some experiences here tutoring, and so I sort of enjoyed working with people and helping them kind of get that light bulb moment when they go, oh, okay. So I decided to go back to school and get my teaching credential, and had all that lined up. And somebody who I'd worked with in a previous job called me to say, you know, there's this boarding school on the East Coast that needs a physics teacher. They have a physics teacher who's being called to active duty for the Gulf War. This was back around 1990. And they're going to need somebody to come in and teach for the rest of the year. And I was thinking, wow, I could teach now and get paid, or I could go to school for a year and a half and keep paying. It seemed like a good idea. So I called the school, and you know, I'm a Carleton grad, I have a physics degree, you know, I'm definitely the right man for the job. And somehow they believed me and they hired me, which is clearly an illustration how desperate the school was to find somebody. So I went out to the East Coast and was driving up to the northwest corner of Connecticut, where Hotchkiss is located, and you know, I come across this beautiful college campus where there's, you know, golf course and big brick buildings, and I thought, wow, this is great, there's a college out here too. And then I'm starting to see signs, and I'm realizing, nah, that's the school. And I was so out of my milieu. I went to a private school in San Francisco and got to get my for high school, but it was 60 kids, and I had no idea about prep school life or any of that. So that was quite a shock to me, and that was sort of my indoctrination into teaching. And I very quickly realized that, wow, I don't know physics nearly as well as I thought I did. And over the first couple of years, I realized that you learn a lot more about physics by teaching it than you ever do by learning it. So if you ever are wanting to really get good at physics, go teach, because having to figure out how to explain something to have it make sense for somebody else is quite a challenge, and I'll talk more about that today. But it was sort of through that first few years of teaching that I really realized that my way of keeping a worldview as a physicist, because that's what having physics goggles is about. It's seeing the world in terms of physics. It's not necessarily solving physics problems or reading the latest research. It's just that every time you see something happening in front of you, the way in which you think about it is from a physicist's point of view. And that's what I strove to give to my students, and still do, is not so much to teach them some physics, that hopefully will happen along the way, but my real goal is sort of help them find their own way into seeing the world as a physicist. And my path to doing that was by teaching. And so that's sort of how I found my physics goggles. And that love affair that I had from staring at the night sky as a teenager needed a way to be expressed. I mean, part of me staying earnest to that was, or honest to that, was to find a way to stay in physics. But it was pretty clear that graduate school wasn't the right route for me. I just wasn't going to go down that path. So some time passed, and I had been in the classroom for a number of years, worked for a number of different independent schools, started to get a little bit, the glory of finding physics goggles was starting to wane a little bit in light of grading and dealing with independent school politics. And so I decided to make a little bit of a change. And so I left the classroom and jumped into the startup world in Silicon Valley, which is right during the peak of the web boom, and worked for a startup for about 6 months, and that was really exciting, but yeah, it wasn't physics, and I was pretty bored, and they paid me a lot of money to do absolutely nothing, and I didn't feel very good about that. So I got out of that, or I should say the company collapsed, and I needed to find another job. And so there was this organization called RAFT, the Resource Area for Teaching, and a colleague passed me the job description of becoming the Director of Education. Now, RAFT is a very interesting place. As Joel mentioned, they were a reuse organization. So what that means is, so for example, a swimsuit manufacturer will be cutting out their swimsuits, and you have a bunch of scrap fabrics, and those go into a barrel somewhere. Lipton Tea Bag Company made their tea bags and bought their string for their tea bags on these cardboard cones. So after the manufacturing process, they'd have lots of these leftover cardboard cones, which had a narrow opening on one end and a nice big opening on another end. Klutz Books, a great activity book company, got a lot of return books, and they believed in Raft, so they held on to all the returns and gave the return books to Raft. So all of this random weird stuff was accumulating, and there was literally a warehouse full of it where a teacher could come and for about $1 fill a shopping bag full of stuff. You know, you could use it for an art project, or with a little clever reimagination, you could use it as a science project. And sort of that was my job, was to help elementary school teachers who might be a little nervous about teaching science or not have the resources. I could say, hey, let me show you this project, and give them all the parts and pieces they need for a couple dollars to go and do some hands-on science in the classroom. And that was really neat. But part of working for a small nonprofit is you sometimes find yourself in situations that you don't really expect. So anyway, I was going to share one of those with you. So yeah. Oh wait.
It's a Raft spectroscope. This will open up a world of light and color for your students.
Hi, I'd like to find out more about this. I teach an after-school science program, and I'm always looking for great activities.
Well, this is a great project. Go ahead and take a look at any light source.
Oh, wow, look at all the rainbows. My students will love the colors.
A spectroscope allows students to see that white light is made up of all the colors in a rainbow. Another way you can use this is to help students compare the rainbows made by different light sources. Let me show you. Take a look first at the sunlight coming through the skylight.
Oh, really bright rainbows.
So you can see all the colors. Now compare that with the light from a fluorescent bulb.
Oh, it's different. There's still the rainbow there, but it's dim, and there's bright bands on it.
It turns out that every light source has its own rainbow. They can compare incandescent bulbs or candlelight, and kids are really amazed to see the differences between the different rainbows. Now, the Raft kit includes enough materials to make 25 spectroscopes. It includes the cardboard tubes, it includes the silver dots, or sticky dots, which cover the ends, and it includes the matching plastic, or diffraction grating, which is what really makes this thing work. So let's go ahead and make one. Go ahead and make a sticky dot, okay? And then you want to hole punch a hole somewhere near the center, but the exact placement doesn't really matter.
That's good.
Yeah. Now you want to take one of the pieces of diffraction grating, and you cut this into pieces that are a little bit smaller, a little bit bigger than the hole punch. Okay, just go ahead and lay that down. All right. Now when you stick that over the end of the tube, you want to try to center the plastic somewhat. It's not, the exact placement doesn't really matter though. Go ahead and push that down. If you want to make that more secure, you can have your students add a wrap of tape around there. Okay. Now there's a couple of different ways you can have your students cover the other end. You can either have them cover a sticky dot and then make a bunch of holes with a push pin or something, or a little bit more careful construction and have them make one with a slit. Go ahead and take a look at the one made with a bunch of holes. That's good for young kids.
Oh, look at that. There's a lot more rainbows.
Of course. It's not hard to do the more detailed comparison. Now compare that to the rainbow that's produced by the slit.
Yes, the rainbow is much wider. It'd be much easier to see the differences.
Exactly, which is really good for older kids if they're doing more careful science. Now you said you taught 1st through 8th grade?
Yes, we teach them all.
And this is a great project because as you see, you can adapt it for different age levels. And in fact, it actually touches the standards for several different grade levels. The Raft spectroscope is a great project for any kid. Pick up a kit at Raft today.
So I didn't see my job was really as a part of a worker. But the really cool part about Raft is that, well, they're still around. And
Hey, you want to see something?
we're not.
Okay. Light and color for your students.
All right.
Hi, I'd like to find out more about this.
Back in that same spot. Okay, so I brought some toys. So I told you to be careful with that because you guys get to make a spectroscope. So just gonna put a handful of these down. So by the way, Joel seriously undersold the audience, so I brought 40 thinking, I have plenty. So if you don't wind up getting a bag of fun, my sincere apologies. But hopefully there's enough, and maybe some of you can share. Got one more. So there's some of you may find a bag with things to assemble.
I guess people back here don't know.
Get it back.
Yeah, I can show you that.
Yes.
Okay, so does people have their bag of fun? Okay, and reading experience. So you'll notice that there may be a couple things in there that look like they have nothing to do with spectrum. So actually, I don't want you to go too far forward in assembling this because we're going to do a little special tweak that wasn't in the video. But go ahead and you'll find the cardboard tube, which used to be the Lipton tea bag cone, but unfortunately, Lipton tea bag no longer does their manufacturing in California. So one of the challenges Raft is having is all the good stuff isn't there anymore. So now what they do is they buy cardboard cones, or cardboard tubes, but get more or less the same thing. So go ahead and take, you'll notice that you'll have the full sticky dot that has the little pieces of diffraction grating already stuck underneath it. And you can go ahead and put that over one end of the tube, but don't fold the paper down. Leave it loosely attached, because we might do a little bit of rotating it after we do the other end. So just kind of stick it on there lightly for now. And after you've done that, find the two little half pieces of adhesive material and go ahead and make a narrow slit at the other end of the tube. I'll give you a minute to do that.
Don't mess it up.
And once you've sort of made your slit to your desired width, go ahead and you can fold that side down. And the next thing that you're going to do is after you've sort of made your slit is go ahead and look through the end with the diffraction grating on it. And you can look out the window, you can look at any light source. And what you should notice is you should notice that there's going to be a number of rainbows. And so the trick is to kind of look through it and hold the tube steady and gently turn the eyepiece until you get a really nicely defined rainbow on either side of the slit. So if you hold the slit horizontally, you'll see a nice rectangular rainbow above and a nice rectangular rainbow below. If you have the slit vertically, you'll see a rainbow to either the left and the right. So once you, as you play around with the alignment of that eyepiece, at some point you'll notice, oh, that looks really good. So when you get to where you can see a really clear rainbow, and you've got your eyepiece in the right alignment, you can go ahead and seal that side down too. So I'll give you a few minutes to mess around and kind of get that the way you like it. And then we'll do some more observing. We'll come to that. That's that. This is Bag of Fun Act 1. We have Bag of Fun Act 2 later. What's that? We're going to use those that Okay, so does everybody have their spectroscope assembled? So what I would like you to do now, I'm actually going to turn the room lights off because I don't want the spurious light from it. And I want you just to focus on the light from the window. And if you want to walk over to the window and look through it, that's not a bad idea. But I want you to look really carefully at the rainbow that's produced by sunlight. And I want you to really look closely, in particular, like what is the order of the color? What color is closest to the slit? I see some of you looking through the slit end of your tube. If you turn it around, you'll get a lot better results. So what color do you see being closest to the slit? Violet, okay. And what color do you see being furthest from the slit? Right, so we've got our friend Roy G. Bibb. I always get those switched around. So we can see all the colors of white light clearly. So sunlight has what's known as a continuous spectrum. So all the colors, all the frequencies of light are represented. If you look at our fluorescence, however, you will see a different rainbow. I'm going to go ahead and close these.
You're supposed to know this stuff.
So as you look at the spectrum, I'd like you to talk to your neighbor and ask them what they see different in that spectrum compared to the rainbow that we saw.
It's going to be different around
Looking at the rainbow.
I want to cool quantum mechanics.
And if you need to remind yourself what you saw before by going over the window, that's fine. Sometimes it's helpful to go back and forth a few times to really see the differences.
It would have been better if we made this look more I suppose you don't want to give little kids a rainbow. That too, yeah.
So I'm going to ask for a volunteer to share their observations. What did you see that was different in the different light sources? Yeah, go ahead.
There were certain colors missing, like yellow.
So you saw gaps in the rainbow. Okay. What are some other things that people noticed that was different about the fluorescence? Yeah.
The colors they're very well defined blocks.
Yeah, and I think that those dark lines in between some of the colors really accentuate. Does anybody know why fluorescents don't produce the same spectrum as visible light, or in fact know why you see the colors you see? Yeah.
The electrons are being excited to an elevated state and jumping back down to one certain state.
But you know specifically what it is about fluorescence. That's exactly right.
I don't know exactly.
So fluorescents are made of mercury, have a lot of mercury in them. So what you're actually seeing, those are the mercury emission lines that you're seeing in the fluorescence. So I have some other light sources here that I thought we would take a look at. So here is compact fluorescence. So what I would like you to tell me is whether we need to be concerned with the environmental issues with these type of bulbs, because these are certainly have problems disposing of these large. We can actually leave some of the fluorescence on if they want to do a back and forth comparison. So compare the spectrum here with the spectrum that you saw in the overhead fluorescence. Do you see differences? What, you mean physics is fun? Yeah. That's what it's supposed to happen, right?
So we're doing another
So what do you think? Do I need to be concerned with this kind of bulb? Does that have the same issues as this one, or is it different material? You see this? Hopefully what you're seeing is you're seeing that, at least when I looked yesterday, things may have changed, but when I looked yesterday, it appeared to me that the spectrum for this bulb was actually quite similar to the spectrum from that bulb. An incandescent bulb will give you a very different result. How many of you ever heard that, when you go shopping, you should always, take your clothes outside before you make a decision about whether to buy them? Have you ever heard that before? That the lighting in a lot of stores is not full spectrum. So the way your clothes will appear when you have all the colors shining in them will be different than when you only have whatever colors happen to be present in the overhead lights in the store. So light sources all have different compositions. So a couple of other interesting light sources that I thought I would share. These are pretty faint, and it's really hard to see them from more than about the second or third row. But I will turn these on. Some of you probably have seen discharge here. Oh, we didn't was that?
Oh no, we did it with a machine. We didn't just like use some fancy measuring tools. Spectroscope.
And again, you're welcome to come down closer if you want to really get a good look at it. Does anybody recognize this spectrum? Hydrogen. How about this one? You may not recognize the spectrum, you may recognize the color of the light. Neon, right? That's a neon tube. So clearly these are different kinds of spectra than what we saw with certainly with the sunlight, which is a continuous spectrum. These are much more selective emission spectrum. The fluorescents have an element both of a continuous, partial continuous spectrum as well as And since this is a physics talk, I really felt it was important that I at least make some attempt to teach a little physics. So although this may be review for many of you, so here's a simple explanation of kind of what's going on here. I love this gift. So this is, there's an astronomy professor at the University of Arizona who has a great website, and I stole this from him. So what we see here is we see a continuous spectrum which is being emitted from a black body, clearly. That was always one of the most puzzling terms to me. How could this be? The sun is white. Why do we call it a black body? Well, a black body is any sort of hot ball of gas that radiates all frequencies. And so we see all the colors of light coming from the sun, much as we saw through our spectroscopes. And if there happens to be an intervening atom, that intervening atom can swallow up one of those colors, and as somebody mentioned, the atom will excite and go to a higher energy level, and then randomly it will de-excite, and the light that it emits will travel in some random direction. So if you're over here and you're staring at the sun and you happen to be looking, this light happens to be traveling through the outer atmospheric layers of the sun, whatever elements are there are going to absorb certain colors, and you will get an absorption spectrum. So some of you may have recognized from the previous slide that what I in fact was displaying in the background here, this is the sun's absorption spectrum. So all these little dark lines represent a particular electron transition in one of the elements surrounding the sun. So a particularly cool story about this is that we discovered helium on the sun before it was ever found actually here on Earth, which is pretty neat. And it was just simply by looking at colored lines. Then the other half of the story is, so if you see an absorption spectrum where you see all the colors minus, you can also see the light that's produced by whatever that atom is when it de-excites and produces an emission spectrum. So what we see when we look at neon or hydrogen is we're seeing the light that's emitted as those electrons jump down to a lower energy level and give off that energy in the form of a particular color of light. And every element sort of has its own fingerprint, as it were, own sort of specific pattern of electron transitions. And that's a pretty cool thing. Okay. So, bag of fun, Act 2. So you may have noticed that in your bag, there was also a marble and a CD that had a pattern on one side and a little foam thing that has a sticker on it. So the order of assembly is you peel the adhesive off of the foam thingy, you put it on the pattern side with the glue exposed on the other side, and then you stick the marble up underneath the CD and it sticks to the adhesive part and you have a spinner. So take your foam, stick it glue side down on your pattern, and then put the marble underneath. It's easier to put everything on and then pick it up. The So you want to touch your
Like, this is what happened. Oh, I got it.
60s, late 60s,
So a couple questions. Did everybody get their disc made okay? Everybody spinning? Great. Now, did you spin it? Follow the instructions? Okay, and just like the monks, right? So what did you see? What? Wait. Stop. Did you say color? Okay, stop the disc for a second, okay? Now, look at that disc. What color is that disc? Yeah, there's no color on there. What are you trying to do? Somebody put this guy in his place being color, really. Anybody else seeing color? Really? Wow. So maybe there is color. How could there be color there? Anybody? I mean, how could that possibly work? I mean, where is color coming from? It's black and white. Where's the color coming from? I mean, how is there color there to start with? What's that? Yeah. So we have white light. Oh, so there's color in the white. Okay. All right. I can buy that. But the interesting part of this. The interesting part of this is kind of how this works. Because this is one of the cool parts about science too, is that this is really cool. And the explanation is really cool, except it may not be the right explanation. We're not really sure, but what we think is happening is it has to do with the with color sensing and sort of with our whole visual process. So the light detection portion of our eyeballs are the rods and the cones. The rods are very light sensitive. It takes, like, literally one photon can be absorbed by a rod, and it will turn that light energy into an electrical signal, which sends as a nerve impulse, and our brain goes, ah, there's light. The cones are a little bit more complicated. The cones are much smaller. You can see there's a smaller structure there. And they have a variety of different sort of photosensitive chemicals in them. There sort of are three primary photosensitive chemicals in the cone. And each of them has sort of a different portion of the spectrum to which it is sensitive. So you can think of the sort of the high frequency, long wavelength, low wavelength, high frequency sensitive cones, the blue cones as it were. And then you also have the sort of longer wavelength, lower frequency sensitive cones, which I can call the red cones, and sort of the green light sensitive, which I'll call the green cones. So depending on what type of light strikes a cone, that whatever chemical happens to be present in that cone will fire a nerve signal. So when the disc is stationary and you're just looking at it, you have, as we've learned from white light, you have red light and green light and blue light all coming to your eye at once. And so each of the cones fires, and your brain goes red, green, blue, oh, that's white. And so you see white light, okay? So when you spin it, and you're seeing those colors, I want you to look closely and notice kind of where you're seeing those colors. Many people see sort of a repeated pattern of colors sort of in concentric circles. So if you follow sort of any one diameter around, you'll see a particular color at that distance from the center, and as you move out or you move in, you'll see sort of a repeating band of colors. So what we think is happening to produce this perception of color is that as the disc spins, basically what's happening is it's going from black to white, black to white, black to white at some kind of flicker rate. There's some kind of frequency at which this sort of, and from a cone's perspective, it's sort of like on, off, on, off, on, off. And the different types of photoreceptors have different recharge rates. You can sort of think of it as sort of like, any of you ever watch like medical shows? You know, where they like, you know, clear, and they push the electrodes down, and you know, you can sort of hear after they, you know, shock the patient, you can sort of hear in the background, you can sort of hear the thing kind of do it as it recharges and gets ready to fire again. And you can sort of think of a nerve firing in sort of the same way. It gets raised to a certain electric potential, electric signal fires, and then there's a certain small amount of time before that nerve cell is ready to fire again. And what happens is, because of the varying timing of the on-off signals for the cones are not able to fire in such a way that your brain is getting all of the light information in a coherent fashion. And so rather than getting red, green, and blue, it might only be like red cone, green cone fires a little bit, and the blue cone isn't ready to fire yet. So the information your brain receives is a partial signal, and you will see whatever color that partial signal is connected to. So that's pretty cool, right? Okay, so getting back to physics goggles. All right, so you've had your fun with toys now. So it's time for me to get back into the meat of my talk, and I have to do so quickly for only 10 minutes. All right, so why am I here today, and what would I like you to walk away with other than a Benham's disc, which is the name of the object you just made, and a spectroscope? I was very fortunate, as all of you, to be at a place where your professors are very much in line with what the author of the paper that I had you read was in terms of being a scientist teacher. All of them are practicing scientists, but their sort of primary, or it sure felt like this to me. I mean, some of them may disagree with that, but it sure seemed to me that their primary reason for being here was to be a teacher and to sort of communicate their passion and express their relationship with physics, in a critical way through being a teacher. And there's not enough people like this doing this. This was written, another reason I chose this article because it was published in 1989, which was the year I graduated. It's almost 25 years ago. And it's even truer today. There is a great lack of interested people who are passionate about science, who want to go on and pursue a career in science, or be able to read an article and make sense out of it and be able to make an educated decision as a citizen. And certainly there's a serious underrepresentation about different kinds of thinking in sciences. There are not enough people from alternative backgrounds, whether that be gender background or from a different culture. And science is sort of the ultimate, has the possibility to be sort of the ultimate, democratic process. The best ideas rise to the surface, but in order to get all the really good ideas on the table, you need a full spectrum of people to kind of make that happen. And so there's just there's a need for more people who are passionate about science, who want to have a relationship with science, via educating. And I guess for me, one of the concerns, concern is too strong a word. I wasn't that together when I was thinking about this as a 20-year-old. But one of the things that was important to me was again, maintaining a really vital relationship with physics. I love physics. I love this way of seeing the world. And, that it wasn't clear that teaching was going to provide that avenue. But let me just say simply that it does. I learn more about physics now as a teacher than, no offense, than I ever did as a student. Because my students are, it's not just my curiosity that's driving my learning, it's theirs. And that's a huge multiplier. So I learn a lot by teaching, not just sort of having to figure out physics as a way of making it accessible, but the questions my students ask and the things that they wonder about really drive me. So sort of in the last few minutes, I want to share some things that I've learned about learning. So real learning happens when you have something in your hand that makes you go, that is neat. What is going on here? I want to figure this out. And so as a teacher, one of the things that I really strive to do, and I hope you recognize what I'm doing, a bag of fun isn't simply a way of filling some time in the talk. It's that this is how I believe that learning happens. Because I bet that at least one of you will take this back to your dorm and go, check this out, and then sit back there smugly and wait for them to try to figure out what's going on, and then be able to give them the perfect explanation or whatever little piece of it you remembered from mine, which has probably equal chance of being right because, as I say, we're not really sure what the answer is. So I think real learning happens when you create a memorable experience that makes you want to dive deeper, and I think that's a really important piece, and that certainly is part of what happened for me here at Carleton. It was really interesting. I bumped into Joel at an alumni event this summer, and had a really nice evening, and sort of we were talking, and I went home that night and started thinking about myself as a teacher and an educator, and I started having like all these points of connection where I realized things that I hold dear in my heart as a teacher, I learned here. So clearly, there were some memorable experiences for me in this learning environment, and that's what I try to create for my students. Another thing that I've learned is that, and I think I hope this is true at Carleton, is that you recognize and celebrate every time you're wrong. Being wrong is a huge learning gift. If you get an answer right, you're done. You know it. Boring. You get it wrong, oh my God. This is a chance to figure something out I didn't know. And this is something that I tell my students all the time. I work with really earnest, eager, hardworking, curious 12, 13-year-old girls. And one of the challenges in our culture is that girls are often told it's really important not to be wrong. But that's the wrong message. It's really important to be wrong. It's important to celebrate being wrong, and then work to figure out the right answer. And as you pursue your own learning path, don't be disappointed when you get something wrong. Celebrate it, because it's really a chance to actually realize that you didn't understand it as well as you thought you did. And if you didn't do your homework well, that's a different story. And then sort of the last piece is, and this is something that I really hold dear to my heart, is that you never know what key is going to unlock the door for a student. I certainly didn't know, and I don't think my teachers necessarily knew exactly what it was that was going to work for me. But they just throw a lot of different stuff, and you hope something sticks. And that sounds sort of scattershot in its approach, but it's what works. And you have to really, if you're going to be a good teacher, you have to really take time to know each of your students and figure out what it is that they need. Do they need a little encouragement? Do they need to learn how to believe that it's okay to be wrong? Some do. Others just need a challenge. They just need to be given the absolute hardest possible problem because they want to do the hardest thing. Other students might need something completely different. So the really cool part about being a teacher is that it's this constant act of creation and getting to know the people in the room with you. And that's a really cool thing. I don't know how much physics is involved with that, but as a life work, it's pretty rewarding. And then just finally, I'd like to just end with a few acknowledgments. So again, it's a big deal for me to be here. Carleton was a very special time in my life, and I've taken away a lot of things from here that I didn't even necessarily realize. So I just want to, first of all, I want to thank Joel for making it personal. I don't know how many of you have had him as a teacher. I had the chance when we were in San Francisco to sort of watch him operate in the alumni setting. And so a student from 15 years past would walk up and say, "Hi, Joel, do you remember me?" And he would immediately start telling a story about that. I couldn't believe it. What he is talking about, making your relationships with your students a personal one and letting them know that you care about them is one of the most important things that I learned as a teacher. And I think that you were somebody who really taught me that lesson well. Cindy came on board to Carleton. I think I was in my sophomore year. And senior year, I went to her senior seminar. She was talking about graduate school and sort of the trials that women face, going on to graduate. And I looked around the room. There were 33 physics majors the year I graduated, 11 of whom were women. And I think the ratio is about the same now. And I was looking around the room and thinking to myself, how could any of these women have trouble? I was the one I was worried about. I was the one who wasn't going to survive graduate school. And it didn't make any sense to me that they should have a harder path. They were the ones who carried me through here. And it was sort of like becoming aware of this sort of social injustice was a really important awakening for me. And it was something that I carried forward as I went through my teaching career and came to understand my own biases and the way those played out in the classroom, and certainly have played a role in coming to really believe in the value of single-sex education for girls. My daughter just graduated from GMS, the school that I teach. And so thank you for opening that door. It's been a really important part of my life. Rich Noer was my advisor, and I learned a lot of physics, and I did not have a very successful approach to my comps. Jumping into a snowbank. God, I still get sweaty at the memory. And yet, when I go back and read my comps paper, I'm really proud of it. And there was a lot of really good thinking in there. And he gave me the space and encouragement and didn't beat me up. I beat myself up plenty. And I left with something that, even to the failures that I experienced, that I really felt successful. And that's a really important lesson that I always try to hold in mind and allow my students to fail successfully. Bill Titus is the person who showed me that there was a way to solve problems, that it wasn't just about getting the right answer. So it was very humorous to me today to be sitting in Joel's physics class, and they're still teaching the same problem-solving steps. Draw a sketch, draw the free body diagram, write down what you know, write down what you don't know, write down the equations that relate to variables. Because it's this exact things that I teach my kids. An awareness of experimental uncertainty, all of that came from Bill. Bruce Thomas, I took modern physics from him. I think it was my sophomore year. And upon returning the first exam, he said, "So if you got 40 or 50%, you're doing pretty well." And it was like, really? Okay. Well, it says B on it. I guess the fact that I missed over half of the points is good. And what I think the lesson for me there was the idea that hard is okay, and that it's okay for things to be too hard, because it's by things being too hard or challenging and really stretching you. That's how you grow as a learner. And there's not, again, it's sort of connected to that whole, there's value in being wrong. There's value in not getting 100%. Because if it's too easy, it's not going to stretch you. And these are all really, sort of key lessons for me. And then finally, I would like to just acknowledge the presence of some very close friends. I've got 2 roommates from junior and senior, Jim and Rich. They were in that photograph from Village House. And Dan McCudden, who was class of '88 and part of a group that I spent a lot of time with. Just want to, and also for all the family and friends who aren't here, because they're it's the people around you that give your life richness and certainly give my life depth. So I'm going to stop. I think I'm supposed to 4:20, right? I'm close enough. I'll stop talking now and just thank you and wish you the best of luck as you go find your own physics goggles. Thank you. So I guess there's snacks and food. Oh, by the way, I meant to put this slide up. If any of you are curious about any of the resources that I use, like you want to go get that gift, or you'd like to read more about how vision works, that resource on the brain from top to bottom is exceptional. Really good. So if you're interested in these things, send me an email at pgrossi@oil and I will send you links.